Okay, so this is AnyLogic, the simulation modeling software. And I have three models opened. The factory model, supply chain model, and the new product diffusion model. Just a quick UI tour of AnyLogic. So, here on the left, we have the projects tree. You can open multiple models in AnyLogic, and every element of the model is available in the project tree, like, let's say, the crane model, the storage model, etc. In the middle, we have the graphical editor, where you put together your animation and, in this case, the process. This is a pure standard, let's say, discrete-event model. This is the manufacturing process of aerated concrete blocks, starting with some preparation, casting. These are elements like delay, queue, move to storage by conveyor. AnyLogic allows for hierarchical modeling, so this block rising area is actually a block defined by the modeler. It's not a standard block, so we can go in and see what's inside, etc. So this is the, I'll expand this window. This is the pure linear discrete-event model of how the concrete blocks are actually manufactured. In AnyLogic, when you select an element, like for example a delay block, and down there you have properties of the elements, like for example delay time, what happens when the entity enters the block, exits the block, capacity of the delay, etc. So you select an element and these properties are displayed there. Here on the right are palettes. For example, if you're a discrete-event modeler, you will be using our enterprise library palette with blocks like source, sink, hold, delay, queue, etc., etc. This should be familiar to anybody who have used other discrete-event tools. All right, so let's just run this model. AnyLogic is based on Java, and both the model development environment and the models it generates. Important thing to mention is you see that the model started in a different window. Models built by AnyLogic are completely separated from the model development environment. Once you've developed the model, you can send it to anybody. You can run it on any other machine where AnyLogic is not installed, so they're not bound anyhow to the model editor. And they actually can be run as applets on the web. If I have time and if I'll manage to get internet connection here, I'll show you how it's done. But anyway, so this is the running model. Model that is ready to run. I'll not change the parameters. I'll just start the model. I'll run it in the fast mode so that it starts to warm up. This is the two-dimensional animation of the manufacturing process. In AnyLogic we have both 2D and 3D. The process here is that the blocks need to be heated in this area, and after that or before that they are cut by this cutting line. I think it's, yeah, right here you can see the blocks are cut into pieces. But we're not really interested in the manufacturing process here. We're just looking at the tool. Let's look at the statistics. Statistics is not yet available because the warm-up, it's not displayed until the warm-up is over. So I run it in the fast mode. And in the meantime, we can choose some other statistics. These are color charts of the showing the statuses of different equipment like cranes, the traversed autoclaves, another crane, tilt table, etc. Cutting lines, and these are the states of the autoclaves, where the concrete blocks are actually baked. Still 22 hours to display statistics. While it's being executed, I'll just show you one thing. Typically for problems like that, somebody gives you the factory floor and displays where is what. So what the modeler does, the modeler would actually mark up the space on top of the factory floor with markup elements, and then bind those elements with the delays and queues and queues blocks, so that the animation is available. Animation in AnyLogic is also hierarchical. Let's say this rising area has its little animation, which then becomes a part of the bigger animation. So anything you do in AnyLogic is actually object-oriented, hierarchical, etc. Let's look at the 8 hours left. Okay, let's wait. Three, 2, 1. Yes. So, okay, we have the utilization of various devices. We have the let's see, time spent by the entity in different zones, and we have the processing log of the main events that are happening. Because in this case, I think the customer wanted to have that log explicitly in the model. So that is a typical discrete event model of a manufacturing process done with AnyLogic. Nothing really special. Look at a completely different model. It's a supply chain model. This is a simplified project, a simplified real project with all data here are actually made up. So what's happening here? We have 1, 2, 3 suppliers of parts. Let's say this is a laptop supply chain. So one supplier supplies, let's say, LCD screen, processor, etc. 2 manufacturers. Several, these yellow guys are distributors, and then the green guys are retailers. They sell laptops to clients, to people, let's say. There are no events and queues here. Everything is implemented as objects, as agents, and agents are connected. You see how the things are transferred along these lines, and you can have this both in 3D and 2D view. The green bar is the inventory at the current at the point, and the red bars, which grow downwards, is the order backlog. Distributors and producers, they choose their suppliers according to the history of relationships. So these agents are really, let's see, smart, they have memory, and they make decisions. What is probably more important here, that we do explicitly model clients. This is a scaled-down model with 150 agents representing clients. So each agent, each green dot, is an agent. It represents 2,000 people. Let's say something bad happens to this producer. See that the inventory goes down and the order backlog starts to grow, but still the dots are green, which means the people can get their orders on time. So if the other producer, okay, so something bad starts happening, the other producer is overloaded with the orders because the supply chain got reconfigured. And you can see that sometimes red dots start to appear. And if something bad happens to that producer as well, then we see that there are big problems. That these red dots are unsatisfied people who are wait too long for their orders to deliver. So this is a combined model of the supply chain and the market. And we can look into, I'll just pause the model, and we can look into the consumers. I can look into each individual consumer. And at the main object. All right. So we won't go into the technology, how we built this model, and what is actually inside the consumers and the suppliers and distributors. The thing to remember is that here, we don't think of a system as of a process. We just, let's say, build models of components, suppliers, producers, distributors, and let them interact. The network of interaction is displayed on this map. By the way, any questions on this or previous model at this time? Not so far. Very good. And the third model is really a simple one. It's a system dynamics model of a new product diffusion.
Sorry,
yeah.
Before you go on this third one, I
Uh-huh.
have a question on the agent-based model. It didn't show actually the model of the agent.
Uh-huh. Yeah, I deliberately did so because in a while we will be building an agent-based model, and I will talk about the languages that you use to build agents, to build agent internals, let's say. So this is something that you will see in the kind of second part of this workshop. So far, my intention is just to show you three different models using three methods, really. So with the system dynamics model, I'll, as long as it will not be the part of our exercise, I'll explain the technology. Okay, we are to model the diffusion of a new product in the market. And what we know is that the size of the market is the 10,000 people. And we know that people are sensitive to advertising and to word of mouth. So what we do, we start building models like this. Okay, here are our potential clients, 10,000 in the beginning. Here are our clients, people who already use our product, 0 in the beginning, because we haven't yet introduced the product to the market. Fortunately, our product will sell, so there's flow from potential clients to clients. This is flow, and these things are called stocks. Compared to discrete event queues, these are not really containers with items in there. They're just quantities, variables. The value of the variable is initially 10,000. We don't have individual people here. What affects sales? Advertising. How does it affect sales? We make an assumption that there is a certain parameter like advertising effectiveness. And let's say each month 1.5% of people buy our product because of advertising. Is that assumption a valid one? I don't know. It depends. It's all left to the modeler. The system dynamics model language is very simple in terms of what you draw, but it's building a system dynamics models requires a great experience and understanding of dynamic systems, because you make a lot of assumptions. This is high level of abstraction. All right, so sales from advertising is the number of potential clients multiplied by that parameter, advertising effectiveness. Where do I get this parameter? Maybe by calibrating the model against the data that is available. Another driver for sales is word of mouth. How does that work? Sorry. People who are already our clients talk to other people, and potentially a client from here may talk to potential client from there. And if that happens, there is a probability that that guy will tell this guy that the product is good and convince him to buy. Therefore, sales of word of mouth have the following equation. Each client, each month, talks to a certain number of other people. This is contact rate, the number of people per month the client talks to. Of those other people, a certain percent is our potential clients, because a client may talk to other clients. So that percent is potential clients divided by the total population. And there is only a few of them that he will convince to buy. Let's run this model. No individuals, only numbers. Potential clients, number of potential clients go down. The number of clients go up. And this is the sales curve. This is a classical bell-shaped and S-shaped curves that anybody who is familiar with the either diffusion models or the theory of dynamic system would immediately recognize here. So initially, we have low sales. Then, as the word of mouth starts to work, sales. This is the sales over time curve. Sales go up, and as the market gets saturated, sales go down. So here we have everybody has become no potential clients. All people are our clients. Sales are zero. So that's the dynamics of the system. And question? No? All right. We managed to model the system only using differential and algebraic equations. Other things that you do with system dynamics model, you do things like sensitivity analysis. For example, how sensitive is this model to the advertising effectiveness? We're varying advertising effectiveness from 0. By the way, under value 0, there will be no sales. So no, because people don't have a reason for the first sale, to 1% to 20%, and this is the sales curve. Other types of experiments include things like compare runs. Let's say with the contract rate 100, I have that kind of dynamics. With the contract rate 10, I have this kind of dynamics, a lot slower adoption, etc. So these are experiments typically done with a system dynamics model. One final remark here. Computational system dynamics models are very efficient. I'm able to run the model in, I don't know, maybe 1 millisecond compared to a typical agent-based or discrete-event model. Because the only thing which is done underneath that graphics is just numeric calculation of differential equation. And the system dynamics model doesn't care whether there are 10,000 people or 10 million people. It will calculate equally fast. So that was a system dynamics model.